Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And as we continue in our series of basic elements of a basic meteorology course or textbook. And today we're going to take a look at the composition of the atmosphere and some details about that composition that you may not be familiar with. And this could actually help with your understanding of how our gases behave and what their radiative properties are and the impact that those gases have on our temperature. So let's start off, first of all, let me put myself down here in the corner, and we'll take a look at all the gases that make up the atmosphere. Now, the biggies are nitrogen and oxygen, roughly 78 and 21% of the atmosphere is made up of those two gases. And then in third place is argon, which is just shy of 1%. Behind that is carbon dioxide, which is 0.042% of the atmosphere. And then you have neon and helium, methane, which is another greenhouse gas, krypton, hydrogen, nitrous oxide, carbon monoxide, I think that's pronounced xenon, ozone, nitrogen dioxide, iodine, and ammonia, making up very, very, very small amounts of the atmosphere overall. Now, if you add water vapor into the mix, in tropical regions, water vapor can take up as much as 4% of the atmosphere. In the polar regions, it's virtually zero, okay? So if at 0%, then the percentages of nitrogen and oxygen and argon hold. But as water vapor becomes more significant in the tropical regions and goes up to 4%, then nitrogen would drop back to 74.96%, oxygen to 20.11, and argon to 0.89. So again, water vapor makes up a different percentage of the atmosphere depending on where you are, and that affects the overall composition of the atmosphere by the other gases, especially nitrogen, oxygen, and argon. So, with carbon dioxide making up only 0.042% of our atmosphere, what in the heck is the big deal about that? Why would we possibly be concerned with something that small? Well, here's the big deal. The current level is 430 parts per million, up from 280 parts per million at the beginning of the Industrial Revolution. Now, what does parts per million mean? It means that for every million molecules that you have, 430 of them are carbon dioxide presently, and that's up from 280. And if you do the math, you divide a million by 430, you get that 0.04%. Now, interestingly enough, in your coffee, about 400 parts per million, not that distant from 430, is made up of caffeine, okay? And we all know that caffeine can have a significant impact on how you feel. So carbon dioxide is increased from 280 parts per million to 430 parts per million today, and that is an increase of roughly 54%. Now, suppose you switch from a coffee with 50% less caffeine to one with a quote-unquote normal amount of caffeine. That, at least for some people, is going to have a very, very significant impact on how you feel, how fast your heart beats, how anxious you feel, and so forth, how easy it is to fall asleep or not easy to fall asleep. And so even though the amount of caffeine compared to the overall liquid of coffee is very, very small, it's still a lot of molecules, and it has a big impact on how you feel. So the actual amount of increase may be small, but the effect on how you feel can be quite significant. Moving on, a single liter of air at sea level at 0 degrees Celsius or 32 degrees Fahrenheit contains 2.7 times 10 to the 22nd molecules. That is 27,000 billion, okay? That's 22 places to the right of the decimal point, okay? That's just in 1 liter of air, okay? Now, what is 430 parts per million of that liter of air, which is the current level of carbon dioxide? It is 11.6 billion molecules of carbon dioxide. Now, that's a small amount compared to 27,000 billion, but that is still a lot of molecules, okay? 4.05 billion molecules have been added since the beginning of the Industrial Revolution. So you have 4, and then you have 05, and then you add another, let's see, 9, 18 places after the decimal point, okay? So you've got 6, you've got 05, which is 2 of them, and so 16 more zeros after that, okay? So with each one of those molecules effectively blocking the transfer of infrared radiation to space, one can easily see that the impact of this increase can be immense, okay? So again, compared to the total number of molecules, it is small, but it is a significant number of molecules nonetheless. And since the radiative property of each one of those molecules is to block outgoing infrared radiation, then you can see how the impact would be quite large. Without carbon dioxide, water vapor, and other greenhouse gases such as methane and nitrous oxide, the Earth's average temperature would be 60 degrees Fahrenheit colder, making our planet an uninhabitable ice ball, okay? So the natural amount of carbon dioxide and nitrous oxide and water vapor is what makes life possible, okay? Those things are not inherently bad in of themselves. They are the reason why we are here, okay? The problem is, is that if you adjust that number by a significant amount, then it starts to upset the balance, the radiation balance of incoming solar radiation to outgoing infrared radiation, okay? And that's where the big problem is here, is that too much of a good thing can turn out to be a bad thing. Now, there is uncertainty in terms of how much warming there will be because there are compensating effects. Like, for instance, if you have more cloud cover, that's going to reflect the amount of incoming solar radiation. If you have lots of volcanic eruptions that put particles into the atmosphere, that is going to obviously reflect some incoming solar radiation. And those are all things that are very, very difficult to predict in advance. And people have made the argument to me, well, the Earth has been warmer than it is now. That's true. There's been more CO2 in the atmosphere than there is now. That is also true. The climate has changed ever since time began on its own. That also is true. The one thing about this is that we have not, so far as we know anyways, ever seen this amount of change in such a short amount of time. These natural changes in our climate have occurred over tens of thousands, if not hundreds of thousands, or even millions of years. So that's very, very different than this occurring over a 150-year period. There is a retired professor of meteorology at MIT, Carrie Emanuel, who is a member of the National Academy of Sciences, and that puts you in the elite group of scientists in the entire world. You don't get into that by accident. I love his approach to this entire topic. He said, Greg, it all boils down to risk assessment, okay? I have often mentioned with tornado warnings that the chance, even if you're under a warning, the chance of that tornado going directly over your house is very, very small. But if it does, and you haven't taken any action to protect yourself, you are screwed, pardon my French, okay? So if there is a way to minimize the risk, which in the case of a tornado warning would be to go to your basement or your interior closet or bathroom, whatever your safe place is, then you have minimized the risk, and what have you given up? 20 minutes of your life. Big deal, okay? So it's the same thing here. If we can figure out a way to minimize the risk without harming people to a significant degree, why isn't that something we could all agree on? And I think that we should all agree on that. There is no reason for political ideologies and falsehoods to get in the way of dealing with real science. And that's what this is. This is real science. It is factual. It's not made up. It's not a hoax, okay? Is there uncertainty? Yes. But let's make sure that we have done everything we can to minimize the risk so that the worst case scenario doesn't occur. All right, sermon over. That is bonus weather video number 2 for this week. Number 3 will be coming up on Friday, and the next daily update, of course, coming up tomorrow. You all have a great Wednesday evening, and we'll talk to you again tomorrow. Take care, everybody. See you later.